Okay, in this video, we're going to go over Chapter 4 Extended, which is going to be the techniques of anti-differentiation. Okay, so a little background. We've already done all the rules of derivatives of functions that we're going to cover. Now we're going to work backwards from the derivative to get the original function. And this process is called anti-differentiation. And it is more precise than using the Riemann sums, which we used in the last lesson. So we're going to call the derivative this time f of x. And the antiderivative is going to be capital F of x. Okay, so get that notation down because that's important. So let me just highlight that. Okay, so here's your derivative and here's your antiderivative. Okay, the first class of integration is indefinite integration. So that's when you have no endpoints. So endpoints for Riemann sums were like the a and the b. So we're not going to have those. Okay, so there are a couple of different techniques we're going to use. We're not going to learn them all for our course, but we are going to do several of them. So the first one is, how do I find the antiderivative when my derivative is a constant? So if you just think about that and you work backwards, all you have to do is add a variable to your constant, and that would make your antiderivative. Now remember, when you take the derivative of a constant itself, right, like the 7, the 10, or the 1,000, that is going to fall away. I'm not going to have that plus 0 here because I don't need it. So therefore, when you work backwards, we can't really get the original function because we're not sure what that initial constant was. So how do we handle this? This is how we handle it. We take the 3 of the x and we add some constant, and we represent that constant as a c to allow for all possible answers. This c is called the constant of integration. Okay, and you're going to see that wherever you have indefinite integration, unless you have more information to use. But plan on always adding it. Okay, so that's one way of doing antiderivatives when you're given a derivative that's a constant. Okay, here's another one. What if you're given a derivative that is a variable? To find the antiderivative of a variable raised to a power. So this is raised to the power of 1. This is what we're going to do. We're going to generalize it here. So if you have x to the r, you're going to take that r and you're going to add 1 to it. Remember, in the taking the derivative, we subtracted 1. So when we do the antiderivative, we're going to add 1. So here's adding 1. Not only are we going to do that, but you're going to create a divisor that's going to be equal to the power your x is now raised to. And then don't forget the constant of integration. Okay, so for this first one, let's see if we're following the rule. I would take the x, I'd raise it to the 2, and I would divide by 2. And I'd add the constant of integration. So you can either write it like I've written it here, okay, or you can write it by pulling out the 1/2. Either way is correct. Okay, so let's further generalize it. And I'm going to do the generalization and then I'll do an example. So if you had some constant and then you had it times x to the r, if that's your derivative, then your original function or your antiderivative, bring the constant along for the ride. Then follow the same procedure. Add 1 to your derivative exponent, and then divide that by the same power, okay? And then plus c. So let's find one. Here's an example. F of x equals, what if I say 7x to the 3rd? Then my capital F of x is going to equal, bring the 7 along. I'm going to do it this way, just for contrast. Put my x down add 1 to it, that gives me a 4, and divide by 4, okay? I like having it that way. If you prefer this way, that's okay. And then don't forget the constant of integration, all right? So now we have 2 things. Here's our third. Finding the antiderivative of a function raised to a power. So I think we just, oh, okay, excuse me. Finding the antiderivative of a function raised to a power. Here's your function. This is the situation when if you were taking the derivative, you would have to use the chain rule. So you're going to have to account for that. So let's figure out what we're going to do. So let's look at the generalization first. If you have some function raised to a power, and that's your derivative, to get the antiderivative, look what's going to happen. You are going to take this function, okay, so this is now a function, and you're going to raise it to the r plus 1. This r plus 1 still goes down. Remember when we took the derivative with the chain rule, we multiplied by that derivative of the inside function. We're going to multiply it again, but we're going to do that down in the denominator. All right, so let's see if we can make sense of this. Let's use this as our example. If this is our example, I'm going to maintain that same function. I'm going to raise it to the 5. I'm going to put a 5 down here, and I'm going to take the chain rule, and instead of multiplying it by 3, I'm going to combine that 3 with the power I just got. Okay, so that gives me the 15, and that's all good. Okay, so just like I had written over here that I didn't mention, if your r is equal to -1, we have a different procedure. Why is that? Because if you put the -1 down here, wouldn't you be forcing yourself to divide by 0, which you cannot do? Okay, so that's our issue there. Okay, so coming over here, what's going to happen now is we're going to look at this and we're going to say, all right, same thing happens here because of the same reason. Okay, now we're ready. We've done 3 different scenarios of taking the antiderivative. We are now ready for the notation that can go along with it. And this is what it is. Instead of writing little f of x and capital F of x, we're now going to use the integration sign. Rewriting our examples gives us this. Okay, so you're going to take the antiderivative of that little f, but I'm just going to write it as 3. Because I'm taking the derivative with respect to x, I am going to have dx be at the back. Okay, so that's one thing. So now get your same answer. You're going to put a constant with it, excuse me, put a variable with it, and then add the constant of integration. Okay, so those are our notations. Notice we have no endpoints still. Okay, the next one, you have x raised to a power, and you have the dx to take the antiderivative, increase that power by 1, and then divide by 6. Okay, and then plus c. Last one is the function raised to a power. You're going to keep the function. Here's your notation. Keep the function, raise the power by 1 to 5, and divide this by not just the 5, but also the 7 from in here. Okay? So that's good. Okay, so we have a couple of other rules. So far we had A, B, C. This is going to be D. So you're going to find the antiderivative when you have E. So how's that going to look? Well, whenever you think about doing it with E, think easy, because look how easy it is. If this is your little f of x, so you're going to take that and you're going to write the exact same thing. See how this is the exact same thing? And then take this coefficient and put it in the bottom. Done. What if you have a constant involved? Constant comes along for the ride. This looks the same. and you're going to divide by the coefficient of the x. Done. So that's why it's easy, but you're going to have to memorize this. Okay, the last thing. Remember I said if you have x to the -1, game over. You can't follow that rule. Well, that's because if you have 1 over x, then that is equivalent to a natural log when you take the antiderivative. Okay? Because remember, we couldn't divide by 0, so this is how we're going to handle it. So now we get natural log of x plus c from our answer. What if we had instead, so this is case E, what if we had instead a, I don't know, 15 over x dx? That's going to give us, the 15 is going to come along for the ride, and we're going to get natural log of x plus c. Okay, so that's how you handle it when you have a constant. Okay, if you have a sum of functions behind the antiderivative sign, or the integration sign, you can break this up to 2 antidifferentiations and then sum them. Okay, so the integral of a sum is the sum of the integrals. If that's the case, after you get the answer, so say you get some answer, you only need to add 1 c at the end. Okay, you don't need to get a series of c's for every integral that you're taking the antiderivative of. Okay, so that's good. All right, so now we're going to do some practice here. So let's look at that. So it's practice taking the antiderivative of an indefinite integral. If I have 8 to the x, what do? I have 8 to the x over 2 divided by 2 plus c. And then I would make that 4x squared plus c. Okay, the next one is going to be, oh, look what I have. I have a natural log scenario. So that's going to be the constant times the natural log of x plus, oh, here's the easy one. Write e to the 7x, just like you see, divide by 7, and now I'm going to add c. Okay, next one. I have a function raised to a power. Take your function, add 1 to the power, take that power down below, and also multiply by the reverse of the chain rule. So what do I get? And then plus c. I get 5x minus 4 raised to the 4th over 20 plus c. Okay, we can't deal with radicals, so we're going to rewrite it first off. So let me do this. Let me come over here and let me say rewrite. So let's rewrite this as 7x all to the 1/3 power dx integration. Okay, so what am I going to do? I'm going to say I have to add the 1, right? So I have my 7x. I'm going to add 1. If I add 1, I'm going to add it as 3 over 3, so that's 4/3. Whatever's down here is going to go down here, and times the 7, which is the reverse of the chain rule, right? Okay, so can I clean that up? 7x to the 4/3, I'm okay with that. But then down below, don't I have 28/3? So why not write that this way so I don't have a double-decker fraction? And then I'm going to say that plus c. So I'm going to stop here because I need to do a second video. So let me stop there.